Have you ever really thought about that invisible force that powers pretty much everything in our lives? It's in the screen you're looking at, the lights in your room. It's electricity. And today, we're going to pull back the curtain and tell the simple story of how it all works. It really all comes down to a super simple question. You flip a switch and boom, a light bulb glows. We do it all the time without a second thought. But what is actually going on inside that wire to make light? It seems like magic, but it's really just some fascinating physics. The best way to get it is to think of it like a story with three main characters. There's a flow, there's a push that gets that flow started, and then there's a friction that kind of fights against it. If you can get your head around those three things, you've pretty much nailed the basics of electricity. Okay, so let's meet our first character, the flow. Now, when we're talking about electricity, we're not talking about water in a river. We're talking about the flow of something totally invisible and incredibly tiny, electric charge. And this flow has an official name, electric current. The river analogy is perfect here. You know how water current is just how much water flows past a certain spot every second? Well, electric current is exactly the same idea. It's just how much electric charge, which we call Q, moves through a wire in a certain amount of time, T. It's this constant massive parade of electrons on the move. And we measure this flow in a unit you've probably heard of called the ampere, or just amp for short. Now get this, 1 single amp is a huge amount of charge. It's what's called 1 coulomb, which is something like 6 quintillion electrons, all flowing past one little point in a single second. I mean, the scale of this flow is just mind-boggling. But here's the thing, right? A flow doesn't just start on its own. Those little charges need a reason, some motivation to get moving. So what is it? What gets them going? Well, that brings us to the second character in our story, the push. Think about it like this for a second. If you have a tube full of water, and it's just lying there perfectly flat on a table, that water isn't going anywhere, is it? It just sits there. Well, the charges inside a wire are exactly the same. They need some sort of nudge. And this is where that water analogy is so helpful. So imagine you take one end of that tube and hook it up to a big tank of water that's held way up high. What did you just do? You created a pressure difference, and instantly that water starts flowing from the high pressure end to the low pressure end. Electricity works on the very same principle, but instead of using gravity, it uses a kind of electric pressure. This electric pressure has a fancy official name, potential difference. But you and I, we know it by its much more common name, voltage. It's really just a measure of the work or energy needed to move a charge from one spot to another. So, in simple terms, it is the push. It's what gets that current flowing in the first place. So here's the key takeaway. A battery? A battery is basically that high-level water tank. Its entire job is to create and maintain that constant push, which we measure in volts, that forces the current to start flowing and keep flowing through the circuit. No battery, no push, no flow. Simple as that. All right, so we've got our flow, the current, and we've got the push that makes it happen, the voltage. But the journey for these electrons, well, it's not exactly a smooth, open highway. There's stuff in the way. They're always facing some kind of opposition. And this is our third and final character, the friction. As electrons try to zip through a wire, they're constantly bumping into and weaving around the atoms that make up the wire itself. It's like trying to run through a really crowded hallway. All those little collisions hinder their movement. This opposition, this electrical friction, has a name: resistance. And you can see just how much the material itself matters by just looking at a few examples here. Silver has incredibly low resistance. It's an absolute superhighway for electrons. Now compare that to something like nichrome, which is the alloy they use in your toaster. Its resistance is much higher, and that's exactly why it glows red hot. And then you've got glass. I mean, its resistance is so ridiculously high that it's a complete dead end. That's what we call an insulator. Now, besides what the wire is made of, a couple of other really simple things affect its resistance. A longer wire? Well, that's a longer, tougher journey for the electrons, so that means more resistance. But a thicker wire is like adding more lanes to the highway. It gives the electrons more room to move, so it actually has less resistance. Okay, we've met our three characters. We have the flow, we have the push, and we have the friction. So now, for the grand finale, how do these things all connect to each other? Well, it turns out there is a single, beautiful, elegant rule that ties it all together. Okay, so let's get our three characters on stage for the final act, shall we? We've got the flow, that's our current. We've got the push, that's our voltage. And we've got the friction. That's our resistance. So what's the connection? What is the relationship between them? If you increase the push, what does that do to the flow? And how does friction fit into all of this? Turns out the connection is, well, it's beautifully simple. Way back in 1827, this physicist, George Simon Ohm, he figured it all out. What he discovered was that for any given wire, the potential difference, remember that's the push, is directly proportional to the current. Or to put it simply, the harder you push, the more flow you get. Kind of makes sense, right?
And he captured this whole relationship in one perfect golden rule. Ohm's law. V equals I times R. Voltage equals current multiplied by resistance. This single, simple equation is the absolute key to understanding pretty much any electric circuit. It perfectly ties our three characters, the push, the flow, and the friction, all together.
So I'm going to leave you with one final thought, just to really lock this in. Using that golden rule, V equals IR, if you keep the resistance of a wire the same, but you double the push, you double the voltage, what do you think happens to the flow? The answer is sitting right there in that beautiful, simple law. And just like that, now you know the story of electricity.